there. And okay, good. So okay, so we spoke about equilibrium the last class. On that aspect, there are two sets of systems that we can talk about, one in constant volume system and the other in constant pressure system. Wherein in the constant volume system, it's the Helmholtz free energy which needs to be minimized for the system to be in equilibrium, and for constant pressure process, it's got to be the free energy, the Gibbs free energy, that needs to be minimum. So, if you could just go back, you can find examples of what we spoke about, in a system, how internal energy has to be minimum and entropy has to be in a maximum situation, so that equilibrium can be obtained. Before we talked about the Helmholtz free energy. So in that sense, let's say I'm not sure, I'm not able to draw things. That's why it's the okay. Let's try and do a drawing if possible. Let's say we can share this. Okay, and that we can do there's a the screen sharing, share whiteboard. Okay, let's try and do something. Okay, do you see a whiteboard? Yeah, guys, do you see a whiteboard? No?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, but then it is still not ready. Yeah, okay. Yeah, let's do that. Okay. Let's try doing something. So let's say if you have a system in a closed container and you have some gas here, right? Okay, and there is a partition. Let's say this is gas A and then this gas B, right? Now let's say, and the volume is fixed, right? I'm just trying to give you an example. Now if this sort of this partition, if it is sort of lifted up, right, and the temperature is kept constant,
सर
then
कुछ
what's
दिख
going to
नहीं रहा
happen?
है. एक्सक्यूज मी सर, कुछ दिख नहीं रहा, केवल वाइट पेज ही आया है.
ओ ये मतलब जो ड्राइंग्स दिख नहीं रहे हैं?
नहीं सर, कुछ
सर
नहीं,
दिख रहे
केवल
हैं सर.
सर
नहीं
दिख
दिख
रहे
रहा है
हैं।
सर.
एक्चुअली जो फोन्स यूज कर रहे हैं थोड़ा राइट को स्क्रॉल कर दो.
Yeah, maybe it's you have to optimize the viewfinder.
ओके ओके सर, दिखा सर, दिखा.
Dekha? Okay.
Now be
It's
sir.
just some it's not a great drawing. I am drawing it on a mouse. Had I used a pen, that would be really I mean, proper drawings can be made. So yeah, let me ask you a question. If there's a in a fixed container, there's a constant temperature, and we have gas A and gas B, initially separated by a wall. Okay, and then what you do is you just lift the wall a little bit, or you completely take it off. What do you think is going to happen? Any responses? Yeah.
सर दोनों जो लाइक कंटेनर में जो गैसेस होंगे, लाइक जो ए और बी है, अगर वॉल्स को हटा दें हम, तो उसके जो गैसेस होंगे वो मिक्स होंगे एक दूसरे के साइड अपने प्रेशर को करने के लिए, इक्वल करने के लिए
Yeah, we'll
दोनों साइड।
say both A and the P is the same. Here it is P and here also it is P. Same pressure is maintained. Pressure भी हम लोग constant रखते हैं. Yeah, what you said is correct. In that if there is a imbalance of pressure, then they'll start mixing. All right. If there is no imbalance of pressure.
सर तो अगर ये ए और बी में जो गैस अगर वो डिफरेंट है तो फिर वो मिक्स होंगे, और अगर डिफरेंट नहीं है तो फिर मिक्स नहीं होंगे, क्योंकि प्रेशर भी सेम है और गैस भी तो सेम है।
Oh, gas. Let's say when we say A and B are different, the gases, then we say that A and B are different gases.
यस सर। तो
Yeah.
अगर सर डिफरेंट गैसेज होंगे तो वो मिक्स होंगे एक दूसरे में, क्योंकि जो
Right.
ए में गैस होगा उसका तो प्रेशर बी के साइड नहीं है ना, तो उधर हो जाएगा अपने प्रेशर को वो कंपनसेट करने के लिए।
Well, it's correct, but it's not correct in the sense that there is no pressure equilibrium that we're talking about here, because pressures are already equilibrated. Okay, that's what I said. Here it is P, here it is also P. So there is no difference in pressure. All right. Only difference is gases, the composition of the gases. This is, let's say, nitrogen, this is argon. And let's talk about perfect gases. There's no interaction between gases. Okay. So what's going to happen is, let's say we have fixed the temperature. That means we have fixed the internal energy. Right. U is constant here. And there is no difference in pressure. There was initially separation, but then there is no separation in stage 2. And we're trying to see what happens to, say, stage 2. Okay. In the situation in stage 2, what will happen is the system, the combined system, will go to a situation where it's something is getting minimized, right? And something will get maximized. And what is that thing will get maximized? If we go back to the conditions that we spoke about, it's the entropy that needs to get maximized. And since we say that the internal energy is not changed, so we are left with one condition to satisfy for equilibrium to occur, right? And that condition is maximization of entropy. And that's theoretically what we learn. But practically also, what you will see here, or what you expect to see here, is that A and B will mix among each other. All right? That means A has got all of this area to be filled, and B has got all of this area to be filled, which before the process, or when there was a separator, B was only confined to this place and A was only confined to this place. So in the process of A and B mixing with each other, the combined system has an increased entropy. All right, and you'd be easily able to mark it if, let's say, if you have a colored gas here and another colored gas here, and then you lift it off and then you see how these two gases intermingle, and then make a combined sort of occupancy of the whole volume, and thereby maximizing entropy. That's I gave you just an example of how maximization of entropy is actually is something that we can visualize, right? Anyway, in the whole process, we only considered here the entropy part, but also we can talk about, instead of this, we can talk about a system where there is some solid, only solid, and there is only what is it? Gases, or it's vapor. Let's say this is lead and this is lead vapor. Okay, and then if they are there in the confined system, then the two extremes of and occupancy is that all of it is solid lead and all of it is gaseous lead, or it's a liquid lead or gaseous lead, and the middle position is that there will be an equilibrium of some lead vapors and some lead liquid. Okay, that's where the equilibrium happens, and the system, depending on the pressure and temperature, remains in equilibrium. So things like this are actually taken care well with uh, the incorporation of idea, that is the Helmholtz free energy or the Gibbs free energy. So essentially, you don't have to worry about internal energy and entropy together or separately, where in a constant volume system, the free energy, the Helmholtz free energy actually takes care of it in a combination. And like that for a constant pressure process, and which actually talks about minimization of enthalpy and maximization of entropy in isolation in different things. Now you can talk about the entire thing in the consideration of the free energy of the system, where the minimization of free energy is where the system is headed towards. Right? Now, if you talk about the closed systems, there are many mathematical formulations you can derive, which actually defines the higher order thermodynamic functions, energy functions, in terms of the common variables, common independent variables, right? And four of those energy functions are really important. Talk about du, that's change in internal energy. Da, which is connected to the constant volume system. um, the Helmholtz free energy, and the enthalpy, which is dH, it's related to constant pressure processes, and there its corresponding free energy function, which is the Gibbs free energy. And these are very fundamental equations. I think it's not very difficult to remember them, but even if you don't remember, you can actually simply calculate it, or derive the expressions from simple first and second law of thermodynamic principles. So let's simply go over that. If you talk about change in internal energy, you know that du is dq minus dw, which comes from the first law. And you know that dq from the second law, we define dq, reversible dq, as TdS, right? Simply because ds is equal to dq by t. So now du becomes TdS minus PdV. This is a fundamental equation for the change in internal energy. All right. Likewise, when you talk about the concept of enthalpy, which includes internal energy and the pressure volume work, and that expands onto, if you talk about the small change in enthalpy, that is dH, is du plus PdV plus VdP by differentiating PV. Now you know that du plus PdV is a kind of formulation of the first law. This PdV is the work itself, the pressure volume work, constant pressure volume work, and that gives you dq plus vdp. Okay, and again, that dq based on the second law is TdS. So you have dH is TdS plus vdp. Okay. Now talking about the free energy counterparts of these energy functions, you talk about dA, and dA, you know that A is u minus Ts, that is du minus TdS minus S dt. And from here, you can find out that since TdS is dq and dq is du plus PdV, so this du minus du plus PdV, I'm sorry, that has to be plus, and the plus of that would be negative. Yeah. So du minus TdS gives you minus PdV, and of course minus SDT comes here. So this is another function for explaining Helmholtz energy in terms of common variables like PV, ST. And likewise, the last one is Gibbs free energy, which is H minus Ts, and that is dG is dH minus TdS minus SDT. And for the dH part, you can expand and put all of these things here. And in the whole expansion, you see that du plus PdV, which is equivalent to dq, which is equivalent to TdS, and here it is TdS. So these two cancel out, and you're left out with dg is vdp minus sdt. Okay, so these four relations are extremely important, and that based on these relationships, we can find out how do we express the most common basic thermodynamic variables uh, in terms of energy, right? So from these equations, you can see that T is something which can be defined by the partial of internal energy and entropy at a constant volume system, or the partial of enthalpy and energy, I'm sorry, enthalpy and entropy in a constant pressure process, right? And something you would see also here is that it's very easy to remember is that we talked about energy conjugates, all right? And you know all of these functions are energy functions. Talk about del U or del H or du or dH or dA or dG. All of these things are energy functions. And for the energy functions, the relationship between the basic thermodynamic variables and energy is through a conjugate energy function. All right. And that conjugate energy for T is S. All right. So when we talk about TdS or SdT, those are in the units, in the dimensions of energy. So it's kind of easy to remember. All right. So what we're trying to do here with this, all of these expressions is that we're trying to compare or find relationships of these basic thermodynamic variables in relationship with energy functions. Right. So you know that internal energy is something is related to the S and V system. In the T domain, the change in internal energy with the change in entropy at constant volume is nothing but temperature. With the same thing, change in enthalpy over change in constant over change in entropy in a constant pressure process is equal to T. So T ds, the relationship is here. Likewise, you could see the relationship of S and T, right? So the corresponding part here is S is equal to the change in free energy, Helmholtz free energy, with the change in temperature at constant volume. All right. So so you see that the change in free energy would always be associated with the constant volume process. With a change in Gibbs free energy would be related to constant pressure process, right? So the change in Gibbs free energy over the change in temperature at constant pressure is equal to entropy. Likewise, you can define volume. Okay. And volume, you know, the conjugate quantity is pressure because you need to get energy here. So volume can be defined as, the change in enthalpy with change in pressure at constant entropy, or the change in Gibbs free energy with change in pressure at a constant temperature. And likewise, like you defined V in relationship with enthalpy and pressure, you can define pressure in relationship with internal energy and volume. And here you know that there's a P and V relationship. Okay, and P in relationship with in a constant entropy process is del U by del V, change in internal energy over change in volume. And the same thing, change in the change in the Helmholtz free energy over change in volume over a constant temperature process is equal to P. And you can derive all of these relationships from these four numbers, right? Okay. And this can be useful by solving complex relationship between thermodynamic functions, where there are so many changes. You want to find a very small expression which in nutshell says all the dependencies. Then we might want to use some of these expressions. Okay. We'll do some of these examples going forward. And let me also give you a slightly a mathematical concept again. Again, we talked about it. Say if there's a function which is a thermodynamic function, let's say z. Z is a thermodynamic function which is influenced by x and y, where x and y both are, let's say, two thermodynamic parameters, thermodynamic variables. Okay, and if z is an exact differential, or is it the means which is a state function which doesn't depend on the way the process goes, but it only depends on the the states. From point 1 to point 2, if it goes, it's only concerned about those two thermodynamic coordinates, but not the coordinates through which the process has gone about from 1 to 2. All right, those are state functions, and the mathematical definition of that is that these are exact differentials. Exact differentials meaning something which is independent, is order agnostic, is independent of the order of differentiation. Let's say del square z by del x del y is equal to del square z by del x del y del x. Okay, so that this is something we have done in the past. Now, if this dz is a function of del z by del x and a constant y multiplied by dx, so del z by del y at constant x multiplied by dy. This is how we express, right? Where we keep y constant and then slightly change x and then see the effect of change of x in the change in z. And likewise, we see exactly the same thing. We keep the x constant and with a small variation in y, which is another thermodynamic parameter. We see the change in z with the change in y, and we sum it up and then see that this is the whole change. If this is what it is, then we can define this del z by del x at constant y as a function L, and del z by del y at constant x as a function M. Okay, now we are able to define something like dz is equal to L dx and M dy. And if this is so, and this g is a state function, that means it's order agnostic in differentiation, then we can write as del L by del y at a constant x is equal to del M by del x at constant y. Okay, this is a mathematical proof. If you want to get deeper into that, we can do that, but later time. And what is more important is that if you're able to if you're dealing with a state function, okay, a thermodynamic quantity, which can be expressed in this form, then the interdependence of these two quantities are going to be expressed like this. As del L by del y at constant x is del M by del x at constant y. Now, take this one, this is the generic formula, and apply all of those things to one of these. Then you will end up getting a series of relationships, okay, which is actually a relationship between the basic thermodynamic variables, which is S, P, and T, and V. All right, here the energy functions are not there. So you can see the interdependence of all of these variables in any kind of processes. Of course, there is a little bit of a restriction onto what will happen if you keep the entropy constant or temperature constant or volume constant or pressure constant, things like that. But then this is the interdependence of all of these basic variables. All right, and application of these things we'll discuss in a separate. That will be too large to talk about, but we'll talk about it. How is it applicable in physical systems? But then it's very important for us to actually understand and remember. This is not something that needs to be marked up, but then we can you can easily actually remember all of those things and reproduce at will. When you desire, you should be able to reproduce. So what it says is that del T by del V at constant entropy is the negative of del P by del S at constant volume. Right? So likewise, we have these four equalities, four equations. We can actually derive it from these four variables given in a matrix form. All right, there's nothing mathematical about it. The way I'm going to tell you right now, it's just an easy way of remembering things. There's no mathematics involved here. I've just given a matrix sign, but it doesn't have anything to do with the matrix. Okay. Now, with this, let's say, let me give you sort of a shortcut rule so that you should be able to derive all of these rules. Let's say if we go like this on the horizontal basis, right? Let's say we go by del S by del P at constant temperature is del V by del T at constant pressure with a negative sign. Where is that relationship? Where is del S by del P? Where is del S by del P? Yeah, here it is. Del S by del P. You mark this one as I say. Del S by del P at constant temperature is del V by del T at a constant pressure. All right. Now let's go this way, because when you go like this, put a negative sign. That's the clue. Let's try another. Let's say if we go like this, so del S by del V at a constant temperature is equal to del P by del T at constant volume. Where is that? Here it is. Okay, as del S by del V at constant temperature is del P by del T at constant volume. Right. Likewise, you can go reverse way. Say del T by del P at constant entropy, which is this, is equal to del V by del S at constant pressure, which is this. And likewise, you go the reverse way, the del T by del V at constant entropy is equal to del P by del S at constant volume with a negative sign. That means when you do the operation on a horizontal basis, put a negative sign. When do it the vertical way, then you don't have to change the signs. So these set of relationships between the basic thermodynamic variables is termed as Maxwell's relationships. All right, and I think it's easy to remember. All right, and we will apply some of these things in solving bigger thermodynamic functions. Okay, now let's talk about something which is called Gibbs-Helmholtz relationship. It tries to connect between the Gibbs free energy and enthalpy, or the Helmholtz free energy and internal energy, because those are the related terms, right? It's fairly simple. Again, it's application of this we'll talk about in different sections in future. There's a basic relationship. Okay. Now we can write here as G is H minus Ts. Okay, G is H minus Ts, as you know. But here let's say instead of entropy, we put the its energy function, right? And you know that dg is vdp minus s dt, and when you do the process in a constant pressure situation, then vdp becomes 0 and dg is left with minus s dt. Therefore, del g by del t, partial of g by t at a constant pressure, is going to be minus entropy. Right? So if you go back to this, what is it? Yeah, dg is vdp minus s dt. Now, if you take a constant pressure process, dp becomes 0. The whole term becomes 0. Now, you take a del g by del t, then you are left with minus s. Right? That's what it is written here. It's not just a simple mathematical formulation. What is del g by del t? Del g by del t is you can say it's a slope in a G versus T diagram. Okay, if you're plotting for a system, it's free energy here, and then it's temperature here on the x-axis. Then if there's a curve is like this, some kind of a curve, then this del G by del T is actually representative of entropy, or negative of entropy. This gives you several clues about how and where the system is headed. Okay, it's not simply mathematics. It's got physical interpretations of that. Okay, so all of those things you'll have to you can think about this. What is entropy? What is entropy in the A versus T curve? It's the same thing. In a A versus T curve in a constant volume process, the slope is talking about entropy here. Likewise, you can physically identify what is volume, what is pressure, and what is temperature. Of course, finding it out within appropriate graphs. Okay, now here, if this is minus S, we replace a minus S here with this term, and we end up with G is H plus T partial G by T at constant pressure. Right? Now, if you divide all of this by T squared, then you get G dt, right? And T dg is what is left here, divided by T squared. And what you do is you take the H this side and get the G this side. So that is left with T dg minus G dt by T square is minus H dt over T square. And this you can actually put it in the form of y by x, a differentiation of y by x, which actually gives you d of G by T over dt is minus H by T square, right? And in a process, if this is about a certain thermodynamic state, this would deal with two states, right? From state 1 to state 2, you talk about, instead of G, you talk about del G, which is G2 minus G1, and correspondingly you talk about H2 minus H1, you represent that with del H. So the d by dt of del G by T is equal to minus enthalpy by minus change in enthalpy by T square. Okay, this is called the Gibbs-Helmholtz equation. Likewise, you can replicate the whole thing in terms of Helmholtz energy, Helmholtz free energy, by writing A is U minus Ts. All right, you write A is U minus Ts, and there also you can, in a constant volume process, you talk about partial A by T, which is minus S, and replace this minus S by this function, and you get something like this. And you divide the whole system by T square, and you get an expression which is like differentiation of y by x, which is equivalent to here d by dt of A by T is minus U by T square. And this expression, when you consider it over a process, then you're left with the d by dt of the change in Helmholtz free energy over temperature is equal to change in internal energy over T square. All right, fairly simple. These two equations are called the Gibbs-Helmholtz equation. All right. So we will talk about composition in another class. Well, let's talk about composition. Okay, now all of these systems that we talked about are simple systems where nothing is going and nothing is coming out. It's kind of closed system, all right? But when you talk about systems where you can add other compositions, other chemical species, all right, and that's where the free energy can be a function of all of these variables. It's not simply the variable a function of only temperature and pressure. It can also be a function of the number of different species, okay, and quantitatively how they are represented by number of moles of the different species. So that's why we write is G is a function of Ni, which is component I, and n number of moles of that, Ni number of moles of that, and J, which is another number of the species J, and K, and things like that. And this is a common or generic representation of many species, influencing the total free energy of the system. You might want to consider this as, let's say, if this is the total value of a basket containing apples, oranges, all right, and some lemon type 1, lemon type 2, lemon type 3, and things like that. It has got a different unit price. This has got a different unit price, and all of these lemons have got different kinds of unit prices. Now, don't you think the total value of the basket of fruits would change when you have 5 apples, 10 oranges, 1 lemon 1, 1 lemon 2, 1 lemon 3, type 3 lemon? The value of this would change if instead of 1 type 1 lemon, I put 3 types of lemons. 3 numbers of type 1 lemon. Or let's say I put 5 numbers of type 2 lemon. Is this going to change? Yes, the total value is going to change. All right. But you would like to find out what is the change in the total value when I change simply this one, or simply this one, or simply this one, or simply this one. I need to know what is the change in the free energy of this system, or the value of this system, right? When I change this one or anything else. And when I sum up all of those changes, then I'll get the total change, not the total value. Total value is there. And what will be the small change if all of those things change? That I can do. And that's what is mathematically written here. Is that dg, that's a change in the free energy of the system. That's a combination of partial g by t when the other variables are kept constant, plus dt, multiplied by dt, like plus partial g by p into dp, where other than pressure, everything else is kept constant, plus partial g by ni, where t, p, and other different components are kept constant. And you keep on adding all of those things, right? And then when nothing of these individual species change, then you simply write something which is dg is vdp minus sdt. That's what we call a closed system, right? We talked about the closed system just before that. Closed system is what? It's an open system where no component goes in or goes out. That's closed system, all right? And you open the closed system, that becomes where different species can go in and go out, right? So all of those things you can write as an expanded form of all individual changes and how it influences the total free energy. All of these things put together. And when you don't change the individual species, what you're left with the closed system, which is dg is vdp minus sdt. All right. I think I should, we'll stop it here today, and let's discuss if we have questions, and then we'll take it up in the next class. Okay. I'm stopping the recording, and we'll take questions.